Section 7.1, solving systems of two equations. We've definitely talked about this before, I think in this class, but in Algebra 2 and Algebra 1, you've been through this, so this shouldn't really be anything new. Example 1, solve using the substitution method. So remember, for the substitution method, we look for if there's a variable that we can really easily solve for in one of our equations. In this one, in our second equation, we can really easily solve for x or y by subtracting the other thing over. So, for example, I could solve the second equation for x, and to do that I would subtract y from both sides, giving me a new equation where x would equal 4 minus y. Then what I do is I say, well, if x equals 4 minus y, then I can take the 4 minus y and I can plug it in where the x is in the first equation. So if I write that out, 2 times 4 minus y, and then I have minus 3y equals 22. So notice everything from this first equation is there, just where the x was, I put 4 minus y. So now I have to distribute and solve. So hopefully this is easy. So subtract 8. At the same time, I can add like terms. Negative 5y equals 22 minus 8 is 14. Divide by negative 5. And we're going to leave this as negative 14 fifths. Now, that's why we want to go back and plug in for x, and the easiest place to do that with substitution is right here where we had already solved for a variable. Now we're going to get x equals 4 minus negative 14 fifths. So notice that's really 4 plus 14 fifths. If I get a common denominator here, this is 4 over 1. I want a 5 on the bottom. So this is 20 fifths plus 14 fifths, which is 34 fifths. And that's what x equals. And then normally we try to write these answers as a point, x comma y, so 34 fifths comma negative 14 fifths. That's our answer. Example 2, there's the second or third section in the homework randomly says solve algebraically, and then it asks you to confirm it graphically. And it's a section where basically we're getting into the fact that these are not lines, but they do intersect. And in this particular case, we can basically use a version of the substitution method in order to solve this algebraically instead of having to go straight to our graph. Sometimes the graph is the best way to find solutions, but this one, it's not so bad. Because these are both y equals, what we can do is we can say, well, if this is what y equals in this one, I can put that right here and that y, and that gives me negative x squared equals x cubed plus x squared. And so to solve this for x, what I would do is get everything to one side. So that means I'm going to add an x squared over. So that gives me x cubed plus 2x squared. To solve this I think has kind of been a while for us. I would factor out the x squared that these have in common, which leaves me with x plus 2. This x squared I set equal to 0 and say that means that x equals 0 if I square root both sides, right? Then that's x equals 0. The x plus 2 here, I set equal to 0 and solve, which means I subtract 2 from both sides, and I get x equals negative 2. So my two x answers for this are 0 and negative 2, but we are actually looking at, if I graph these two things, what are the points where these intersect? And so we need y values to go with each of these x's. So I would take like the easier equation here, this one, and I would say, okay, let me plug in 0 and see what I get. If I plug in 0, I get 0, which means one of my solutions is 0, 0. Then I'm going to plug in negative 2. So negative 2 squared. Remember that whenever you plug in a negative number, you put it in parentheses. And here I would square before I take the negative into account. So -2, when I square it, becomes +4, but there's a negative in front, which makes it a -4. So that means that my other point is -2, -4. So I have two answers here, -2, -4, and 0, 0. And then we could graph both of these, put them both in y equals, and look at your graph and see if that really matches up. Example 3, we're going to look at the elimination method. It goes by their names as well. The most common one, I think, would be the addition method or the linear combination method. So it all means the same thing, is that we're basically going to try to add these two equations together in such a way where we end up eliminating a variable. The way we do that is we try to get the same number in front of each of the variables. Like in this case, I'm going to go for the y's. I want the same number in front of both of these y's, but I want them to have opposite signs, so that when I add them together, one's a positive, one's a negative, which means they cancel out. So I would look at this and say, well, this first equation, if I multiply it by 2, I get a 4 in front of y, which is going to cancel out my y's. So to do that, I have to multiply all of the top equation by 2. So I'm going to write it underneath here. That gives me 6x minus 4y equals 16. Now I add coming down on my equation. So I add my x's together. 5x plus 6x is 11x. 4y minus 4y canceled out. 28 plus 16 is 44. Then just finish solving. Divide by 11. X equals 4. Now I want to go back and in one of these two equations plug in, well, really I can plug this into any equation, plug in this 4. So it doesn't matter which one you pick. Sometimes there's an easier one to plug into, but in this case they're all pretty much the same. So I'm just going to plug into the first one. So 3 times 4 is 12, minus 2y equals 8. Subtract the 12. This is a simple two-step equation. Minus 2y equals -4. Divide by -2's. Y equals +2. So then we'd write this as a point, 4, 2. No big deal. We like elimination. We've been doing elimination for a while, so awesome. The next thing we want to talk about, and again, this should be a reminder, is that sometimes there's special cases with, especially dealing with lines, when two lines are involved, that we basically have been doing examples where this first case, that our answer is some variable equals a number, so we were getting like x equals something or y equals number. It solves like normal, nothing weird happens. What it means graphically is your graphs intersect. You have two lines, they intersect at a point, and that's your answer. There's two other cases. One case we would answer no solution. And what that looks like is that as you're working at the problem, the variables cancel out, both of them. And what you're left with is something that's a false statement. And what that means graphically is that you've got two parallel lines. No solution means the lines don't intersect, which means they have to be parallel. Infinitely many solutions is to say that there's like a whole lot of different solutions, like 2, 4 could be a solution, but then there could be a whole bunch of other solutions as well. That's what that term means. So that looks like the variables cancel out, and what you're left with is a true statement. And then graphically, that gives you two equations that graph the same graph. So with lines, that means they're the exact same line whenever it comes right down to it. So example 4 and 5, we're going to solve using substitution or elimination, and we're going to see what actually happens with no solution and infinitely many solutions. So on this first one, I want to do substitution. And you could pick either one if you were doing this yourself, but I'm going to pick substitution because I wanted to point out to you, when is it a good idea to pick substitution? Well, I can really easily solve for x here. And in fact, if I'm lazy, I can just say, oh, I'm going to move this over here. I didn't even have to rewrite the whole equation. And now I can say, all right, I'm putting that right there where x was, -2 times 6 plus 3y plus 6y equals 4. Distribute, -12 minus 6y plus 6y equals 4. So, hey look, negative 6y plus 6y is 0. So I get negative 12 equals 4. So this is where we ask ourselves, does negative 12 equal 4? The answer is no. So this is no solution. We canceled out our variables. They went away, all of them. There wasn't an x or a y, but this is a false statement, so it's no solution. So now when we're going to solve this one with elimination. The easiest thing to do here would be to multiply the second equation by 2, or technically, I don't know if you knew this, but like if you think about it on this first one, we could divide the first one by 2 if we wanted to, and that technically works out. It's really like we're multiplying by a 1/2, but you know, that might sometimes be easier, is to divide by something instead of multiplying by something. But I'm going to multiply this one by 2, and that gives me negative 2x plus 4y equals negative 8. And then once we multiply, like, we're not using this one now, so if it helps you to mark it out so that now you can do your addition correctly, then that's great. 2x minus 2x cancels. Negative 4y plus 4y cancels. 8 minus 8 cancels. Now when you're doing elimination, if I cancel everything out on the left side, there's really a 0 there. If I cancel everything out that's on the right side, there's really a 0 there. 0 equals 0, besides making what kind of looks like a face. 0 equals 0 is a true statement. 0 really is 0, and so that is infinitely many solutions. And yes, I want you to write it out. No, I will not accept you saying it's infinity. The answer is not infinity. It's infinitely many solutions. I'm not making you tell me all the solutions, because guess what? There are infinitely many of them. But I expect you to write that out and remember that.
Now let's look at solving graphically. So here's example 6. We've got an interesting set of equations here. You may notice that this first equation, x squared plus y squared equals 9, that's a circle. And then this next one will give us a line because there's not any squareds in it and there's an x and a y. So if we want to solve the system graphically, and more importantly, we want to use our graphing calculator to help us, the first thing we have to do is solve both equations for y. So on this first one, I'd subtract the x squared over to start off, and that gives me y squared equals 9 minus x squared, and then I would square root both sides. And remember, if you're solving an equation and you square root, you have to put a plus or minus in front of that square root. And so when you graph this, you put this into 2y equals. So you have like y1, and you put in a positive square root of 9 minus x squared. And then you do y2, and you do negative 9 minus x squared. Then we solve the second one, and so I would subtract 4x over to the right side, and then divide by negative 6. That gives me 2/3 x, and then a negative 2. And so this is going to be in the y3 spot. So let's go over to our calculator, and let's put these in. Go to y equals we're going to clear out what we have and put in second square root 9 minus x squared. And then we're going to put a negative square root 9 minus x squared. By the way, you cannot simplify the square root of 9 minus x squared. It is not 3 minus x or 3 plus x. You have to leave it the way it is. And then y3 was 2/3 x minus 2. I'm going to zoom 6 to get a standard window. And so I have mine apparently on graph simultaneously, so they all showed up at once. If you have it where it does it sequentially, then you can actually see what is being graphed when. So Notice the top half of my circle was graphed first, then the bottom half of my circle, and then the line. Now when we find intersection points on our calculator, we go to second trace, and we go down to intersect, and it asks us first curve. And so we're going to start off by finding this bottom intersection because it's going to be easier to find. The first curve that we want is we want to pick either this part of the circle down here or we want to pick the line. We do not want to pick the top of the circle because that's not going to tell us anything about this intersection. So I'm going to press the down button so that this bottom part of my circle is being used. And then for my second curve, I'm using the line because those are the two things that are intersecting. When you guess, it can be helpful to go over to a little closer to the intersection and press enter. And it tells me that this intersection is at negative 1.153, comma, negative 2.769. So negative 1.153 for our x and negative 2.769. Okay, that's one of our points, but we've got another intersection. So the problem here is that this intersection is right here at 3, 0. That's what it looks like at least, right? And we could even trace over here and get really close to it. The problem though is that we took a square root and the calculator doesn't like that, and so if we actually try to find this intersection, it's going to give us an error. And so if you're in the situation where you've taken the square root on both sides and you end up with a plus or minus, we know that this is at 3, 0. We can check it. Like by looking back at these two equations that we started off with, if you put in a 3 and a 0, 3 for x and a 0 for y, it does work out. 3 squared is 9 plus 0 is 9. If you put it in here, then you get 12 minus 0 is 12. So the square root makes it a little tricky if you can tell where it looks like it is, and then that's why we're supporting our answer mathematically, or it actually might say numerically in the book. That's what we're talking about, is to go back in and plug it in. And we can do the same thing for these 2 points, even though we did actually find them on the calculator. We could do this squared plus this squared, and we should in fact get 9. 4 times x minus 6 times y, we should get 12. So that's all there is to it except for the word problems.